So previously we've looked at Dijkstra's algorithm, right, which solves the single source shortest path problem in a weighted graph, but it had a few limitations. So the biggest limitation is that it doesn't deal with negative weight edges. There are some algorithms that will solve single source shortest path problem for graphs even with negative weight edges in VE time. So Dijkstra solves it in E times log V, so these do E times V. So you can look these up if you want. There's the Bellman-Ford algorithm and Johnson's algorithm, both do that. We're going to look at a different algorithm today that can deal with negative weight edges, but also actually solves the all pairs shortest path problem. That is, once we run this algorithm, we can figure out the shortest path between any 2 points in the graph, not just from a single start vertex to anywhere else. Okay, so this is called the Floyd-Warshall algorithm. So, right, and the problem is, as input, we're given a weighted, directed graph G, and the weights can be negative. Weights can be negative. And as output, we want like a 2D array where we'll say S of U comma V is the length of a shortest path from U to V. Length of a shortest path from U to V. That's the basic version. In general, we might want to actually be able to reconstruct, a shortest path from U to V, and we'll see how we can do that as well. Now, one thing to talk about first, right, is that if there's negative weight edges, there might be some cycles where the total weight of the cycle is negative, and that means if you can get to that cycle, you can go around it any number of times and make your weight as small as you want. You can just keep decreasing it forever. So in that case, the notion of a shortest path actually isn't even well defined. Or you could say the shortest path is negative infinity because you could just keep going around that cycle as much as you want. And we'll see that actually this algorithm can kind of detect that situation. So we'll actually know afterwards, are all the shortest paths well defined, or could there be some where there's negative cycles? Okay. So how are we going to do this? So we've been talking about dynamic programming, and so this is essentially a dynamic programming algorithm. So as typical, we're going to introduce another parameter to kind of help us look at subproblems. So in particular, I want to consider, I'm going to add a parameter k. So S of U V K, I'm going to define to be the length of a shortest path from U to V, but restricted a little bit, using only vertices 1 to k as intermediate nodes, running out of space here, intermediate nodes. Okay, so I'm assuming that the vertices of our graph are numbered from 1 through n. Maybe I should say that. Vertices 1 through n. Okay, so if I have my u and I have my v, right, I might have some shortest path between them, except the shortest path that only uses, might go through vertex 2 and vertex 5, certain vertices, but if I'm only allowed to go through vertices numbered 1 through k, what's the best I can do? It might not be the total, the overall best. There might be some better path that goes through, vertex k plus 1. But if I only allow myself to use vertices 1 through k, then what's the best I can do? And our goal is to come up with a recurrence for this thing. So our goal is a recurrence for S U V K. Okay, let's think about some base cases first. And maybe you want to pause the video and think about what would be some base cases you could write down for this. So S U V, and the base cases are all going to have to do with when k is 0. Okay, so k is 0, that means we're not allowed to use any intermediate vertices at all on our path from u to v. So, well, what could that look like? There's a few cases. So, first of all, if u and v are the same, if u equals v, then I'm just looking for a path from a vertex to itself, and I'm not allowed to use any intermediate vertices. Which means in particular I can't go around a negative cycle, right? There might be a negative cycle from u back to itself that would be, even smaller than 0, but if I'm not allowed to use any intermediate vertices, all I can do is stay at u, and the shortest path, the shortest length is going to be 0. So this is going to be 0 if u equals v. Also, if there's actually an edge from u to v, I can go directly from u to v without going through any intermediate vertices, and so just whatever the weight of that edge is going to be the best I can do. So this is going to be w sub uv if, I'll say if uv is an element of the set of edges E. Okay, and otherwise, so in any other case, I have some u and v, they're not connected by an edge. There's no way to get from u to v without using any intermediate vertices, so we're just going to say the shortest distance is infinity, positive infinity, because that's the same as saying that there's no way to get there. So positive infinity otherwise. Okay, so those are our base cases. Let's think about the general case, right? So if I have S U V K, well, so I'm trying to think about what's the shortest length path from u to v where I'm only allowed to use vertices 1 through k. And we're going to do something similar, a similar thought process as we did for the subset sum problem, right, where we were only allowing ourselves to use items x1 through xk, and we said, well, let's think about that last item, xk. Should we use it or not? And so the same thing here. We're only allowing ourselves to use vertices 1 through k as intermediate nodes in our path. And we're going to think, should we use vertex k or not? If we don't use vertex k, then we can just say, well, just look at s u v k minus 1. Like, what's the best you can do getting from u to v where you only allow yourself to use vertices 1 through k minus 1? So I'm going to say we're going to take a minimum of these two choices, right? So this could be s u v k minus 1, right? So this means, don't use k. What if we do use k? So I'm going to draw a picture here. It's going to be helpful. So I'm looking for a path from u to v, and somewhere along the way I use vertex k. Well, in that case, so the best path from u to v through k is going to be composed of these two paths, right? One path from u to k, and one path from k to v. And clearly, the best overall is going to be, the best thing from u to k plus the best thing from k to v. And this path from u to k won't use vertex k. It'll only use vertices 1 through k minus 1. And the same for this one, because we already have a k here. So this is going to be then s of u v, the best path length from u to k using only vertices up to k minus 1, plus whatever the best length is from k to v using only k minus 1. Okay, so that's our recurrence. Now, so we could implement this basically by making a 3D array. right? It's indexed by, basically it's an n by n by n 3D array. The first two indices tell us which vertices you're looking at, and the last one tells us, 0 through n, how many vertices are we allowed to use. And then we could loop over the whole thing and fill them in. As an optimization, it turns out we really only need a 2D array, and we can just basically overwrite it n times. So instead of explicitly storing this k, we just do this thing k times, because every time we fill out ubk, we're only looking at values from k minus 1. Also, because it kind of like, one possibility is this thing is just copied from the previous time, right? Or we pick this if it gets smaller. So that means every entry in the array is only going to ever be getting smaller. And so it's totally okay to just keep overwriting it every time and just look up in the same array. I feel like maybe that's not a great explanation of why that's okay, but you can maybe try some examples and think about why that's the case. But just as an optimization, just a space optimization, it doesn't make the algorithm any faster, but we can just use a 2D array and just do it k times. So the code would look something kind of like this. So we would say, after we fill in the base cases, we would say for k going from 1 up to n, and then for u, we look at all the possible u's, 1 to n, for v, 1 to n. Then we would just say suv is the min of itself, and s of uk plus s of kv. Okay, that's it. So right, it might stay the same if that's still smaller, or we try adding up, the smallest path we know of so far from u to k, plus the smallest path we know of from k to v, and we see if that gets us something smaller. And we just do this, for every k, for every u and v. So analyzing how long this takes is actually super easy, right? This is like, data structure student's dream. It's just literally 3 nested loops that all go from 1 to n. So very obviously, this takes theta of n cubed time. Right, well, and of course this is only taking constant time. We're looking up some things in the array, we're doing a minimum, that's all. Okay, and n, I guess n here is our v, is the number of vertices. So this takes v cubed time, which is interesting because notice it doesn't depend on how many edges there are at all, which is sort of interesting. Most of the other graph algorithms we've talked about, they depend on how many vertices and how many edges there are. And v cubed, actually, that sounds bad, but when you think about, I said there's these other algorithms that can do single source shortest paths when there's negative weight edges, and they take time ve. But e could be as big as v squared, and so in that case it would be v cubed. So this is apparently solving the all pairs shortest path problem, and if you have a dense graph, it's not any slower. And actually this, when you implement this in practice, this is really fast actually. Like the constant factor is very small, because all you're doing is you're doing like an addition and a minimum operation each time through the loop, so it's extremely fast. All right, let's talk a little bit about what if we want to actually reconstruct the shortest path. So so far this just tells us, after we do this, we can look up s of uv for some vertices and we get the length of a shortest path. What if we actually want to know a shortest path? So one thing we could do, as we usually do with dynamic programming algorithms, is right here we took a minimum and we didn't remember which one was smaller. And if we just make like a big 3D array of booleans, so at each step where we take a minimum, we just remember which one of these was smaller and we set our boolean to true or false. Right, so maybe true means, oh, we definitely should use vertex k as an intermediate node in our path. And then false means, yeah, we shouldn't use it. We should just use only 1 through k minus 1. And then we could, using that, we could go backwards and reconstruct what the best path is. It's a nice little exercise actually to write that. I would encourage you to try doing that. You basically, if it's true, you say, all right, we're going to, K is an intermediate node, and now we're going to recursively figure out what's the best path from U to K and the best path from K to V. And you keep going like that. However, I'm going to show you a nice trick that actually gets the job done a little nicer. So essentially the idea is something very similar to what we've done with other graph search algorithms that are keeping some kind of parent map. So we kind of are going to have a 2D parent map. So let me show you how that's going to work. So we're going to have, we'll call it next UV equal the next intermediate node, or the next node in a shortest path from U to V. Okay, and I claim this is going to be enough to reconstruct shortest paths, because if I'm looking for the shortest path from U to V, then I just look up next UV and it says, Q. Right? Q is the next, if you start at U, the next place you should go is Q. Well, now what I do is now I look up next QV, because now I'm looking for a shortest path from Q to V. And that says, oh, that's some other vertex. I just keep doing that. Just like we would iterate looking up the parent of the parent of the parent to find paths, like if we'd done a BFS or something like that. And when we finally get V, if I say, what's next UV, and it says V, then I know that I'm done, right? It says, oh, the next thing is you just literally go to V and you're done. So how are we going to maintain this? Well, in the base case, we're going to set next UV to V for every edge. Right? That corresponds to this base case here. We said if we actually have an edge, then we're going to say, well, the best path we know of so far is just to take that edge. And so, our next will say that the best thing we know of is if you're trying to go from U to V, just go directly to V. We don't really need to worry about this case, like next UU, because we'll already know that if we have a vertex is the same as itself, or if I'm just trying to get from U to U, I just know that I don't need to go anywhere. It doesn't matter what we set next UV to otherwise. And then when we say, if SUK plus SKV, so this is in this step of the algorithm, is less than SUV. Right, so this means this is the best path we knew of from U to V before, and then we just found out that, oh, actually it's shorter if I take a detour through K. So if I do the best path from U to K, followed by the best path from K to V, that gets me a better path from U to V. So all we need to do in this case is change next UV. Right now, the first step along the best path from U to V is whatever the first step is along the path from U to K. Because I'm going to start out by following this path, and then later I'm going to do this path. So then set next UV, right, we're going to set it to next UK. And that's it. It's very simple, and that works if we keep doing this. So we would need to change this a little bit. We can't just do a min, because we need to have an if that says, okay, which of these is the case, and if this one is smaller, then I need to update next, and update SUV. So yeah, there's a nicer version of that written out in the lecture notes, which you are welcome to look at. That's it. That's the Floyd-Warshall algorithm. It turns out there's a few other nice things about this algorithm. So one cool thing is kind of similar to how I mentioned that Dijkstra's algorithm can be generalized to find not just shortest paths, but kind of best paths in a more general sense. You can replace, some of the operations like adding and minimum with other operations, and it still works. So in some sense, the Floyd-Warshall algorithm is actually even more general. There's a huge ton of stuff. So basically any, I'm not sure, any semi-ring, I don't know. There's a huge variety of things you can kind of replace these operations with and get something that that finds paths in best paths in some appropriate sense. So I have a list here. It can find like most reliable paths, largest capacity paths. It can count the number of paths. There's also stuff about like converting DFAs into regular expressions. If you've taken theory of computation, you know what that is. Computing transitive closures. You can actually even use it to invert matrices and solve linear systems of equations, which sounds crazy. Like, what does that have to do with finding paths in a graph? But if you're curious about that, you can ask me or look it up. But this algorithm actually gets used for a ton of different stuff.